Welcome back. Let's continue on chapter 11, section 6. Today we're going to talk about absolute convergence and the ratio and root test. So let's figure out what is absolute convergence. So last time we talked about alternating series where AIs it could be positive or negative. Absolute convergence is basically if you're dealing with a series of AN, summation of AN, and we say this summation is absolutely convergent if the series of the absolute values of this AN is convergent. So we make all the terms to be positive, then we look at that summation. If that summation convergence, then we can say the sum of ANs are convergent. If the ANs are all positive already, then the absolute convergent and convergent would be exactly the same. So a series AN is called conditionally convergent on the other side if this series is convergent but not the absolute value. So the series by itself, it is convergent. So the series is convergent, but not the absolute value of it. Which means it is not absolutely convergent while it is conditionally convergent, or its summation of ANs by itself would be convergent. Okay, we'll see an example of each one just to make sure you understand it. So here's the first example, summation of n from 1 to infinity of negative 1 to the power n divided by n squared. As you remember, this is an alternating series where the terms are negative 1 divided by 1 plus 1 divided by 4 minus 1 divided by 9 and so on. So we're dealing with the alternating series. And an in this case, it's negative 1 to the power n divided by n squared. If we take an absolute value of this an and look at the summation of the absolute value of an, it's basically saying that ignore the signs plus or minus. So basically you deal with summation of, instead of negative 1 to the power n, you just simply have 1 divided by n squared. N from 1 to infinity. And then, is this series convergent or divergent? That would be the question. And we already know that by p-series test, if the power of the n is greater than 1, we know that definitely is a convergent series. So this is a convergent series. And so I can say that an, summation of an is absolutely convergent. Okay, so that means that if we take the absolute value, the summation is still convergent. That's what it means. So they have absolute convergence. So this is the first case that we have absolutely convergent just because the sigma of the absolute value were convergent. This was a true state. On the other side, let's look at this example. If we have summation of negative 1 to the power n minus 1 divided by n and from 1 to infinity, and we're looking at convergence or divergence of this series, we can say, okay, let's first figure out this absolute value of this series looks like. So an, by the way, I can write a couple of terms of this series. It'd be 1 divided by 1 minus 1 divided by 2 plus 1 divided by 3 minus 1 divided by 4. So ANs are basically negative 1 to the power n minus 1 divided by n. This is what the ANs. And summation of absolute value of ANs means ignore the negative power. It would be summation of 1 divided by n. And this is the same as exactly the same series, but every term is positive. That's the absolute value. It makes every term to be positive. So now, is this series convergent or divergent? As we know, this is again by p-series. This is a p-series where p in this case equals 1. The exponent of n is 1. So what we know is that if p is equal to 1, then we're dealing with a divergent series. So summation of ANs or absolute value of ANs are divergent. How about the summation of ANs? Is that convergent or maybe it is not convergent? And last time we kind of discussed this. And we said that if we're dealing with this series by the alternating series test, if you remember, this we created a Bn where Bn was basically 1 divided by n, ignoring this negative 1 to the power n minus 1. So Bn's had to satisfy two conditions. One was being decreasing, which is a true statement in this case, and the other one was to calculate the limit of Bn as n approaches to infinity. And that limit is 0 in this case. And that was the other condition. And we know that if we satisfy those two conditions from last section, then basically summation of negative 1 to the power n minus 1 Bn, which is exactly the same as summation of An's in this case, is convergent. So what we have is we have a convergent series where the absolute value is not convergent. We learned that the absolute value is divergent while the summation of An's are convergent. If that happens, then we're dealing with a if that happens, then we're dealing with a conditionally convergent. What is conditionally convergent? Summation of An's. Means if you put an absolute value there, it wouldn't be convergent. In the last example, I didn't really mention this, but here the summation of the absolute values were convergent, and we already know that the summation of An's are also convergent. You can say this summation of An's are also convergent. Why is that? You can ask yourself why is that? It's by the same idea, by the same token that if we calculate this is a Bn's were decreasing by the decreasing, and then on the other side we had limit of Bn's approach to 0 as n approaches to infinity. It was the alternating test as well, so it implied that summation of An's were convergent. But it turns out that we don't really need to check this. If we check the absolute value and we see that the absolute value is convergent, that means if we have an absolute convergence for the if the sigma of the absolute value are convergent, then the summation of An would be absolutely convergent. You don't really need to check for the An. That is a given. That is basically the absolute. Here's the theorem. Theorem is if the series of An is absolutely convergent, that means the absolute value is convergent, then the series itself is also convergent. Okay, this is a given, so we didn't really need to check it. Okay, that means if the summation of the absolute value for N converge, if this is the case, then definitely summation of An is convergent. This is quite easy to see because you're adding all the positive numbers. If you're adding and subtracting, definitely that would be convergent also. Okay, so here as an example, let's look at this example. Summation of n from 1 to infinity of cosine n divided by n squared. So here it's kind of difficult for me to write the terms because cosine of 1 it would be a decimal value. So what is important about this series is that if you're dealing with summation of cosine of n divided by n squared, you'll end up with sometime a positive number, something like positive cosine 1 divided by 1 squared plus cosine 2 divided by 2 squared, and so on. Cosine 3, I'm not gonna write every term, but just give you an idea. Cosine of 1 is a positive number, so this is a positive number. I should write it plus. It turns out that cosine of 2 is negative on the other side. Cosine of 3 also is a negative number. So what you have is a bunch of positive numbers, some positive, some negative numbers. It's not definitely alternating, but sometimes you have positive, sometimes you have negative numbers. And then you want to figure out, is this really absolutely convergent or not? What we can say, or it is convergent by itself. You can test for the absolute convergency first. Let's deal with the absolute value of cosine n divided by n squared. N squared was positive, so I kept it out of the absolute value. It didn't really make any difference. N from 1 to infinity. Let's check for this. And what do we know about cosine? Cosine is always less than 1 or greater than 0. So what we absolute value of it is less than 1. So I can say this is for sure is less than or equal to summation of 1 divided by n squared, as n from 1 to infinity. This is since cosine of n is less than. This is kind of the comparison test. And what do I know about this series? This is a p series. This is a p series where p equals to 2. So therefore this series is convergent. And if this series is convergent, this guy is less than that. So that must be also convergent. Okay, so this is quite the case. We found out that the absolute value also converges. So the absolute summation of the absolute value of an is convergent. This is what we showed. So that means summation of an's are absolutely convergent. And by the theorem that we had, by this theorem, if the summation of an's are absolutely convergent, then itself it is convergent. And that's quite the given. Then I can say this summation of an is convergent. Okay. The moment that you figure out that this absolute value is convergent, this is also a given always. Okay, here's some test that gives us some idea about the absolute value for this absolute convergency or not. So here, the ratio test, one of the important tests that we use for absolute convergency. So if we're dealing with, this is all for summation of an as n from 1 to infinity. I should have written this. If we're dealing with this series, we can look at the ratio. What do I mean by ratio? We can look at the term an plus 1 and an, and we calculate that ratio. So we calculate the ratio of an plus 1 to an, and we take an absolute value of that. We figure out what is that ratio. If that ratio is a number less than 1, then the series of an is absolutely convergent. If that ratio is a number greater than 1, then the series is divergent. And if it is a 1, this is the important part. If the ratio turns out to be 1, then this ratio test is inconclusive. We can't say anything. Sometimes it is convergent, sometimes it is divergent. We can't say use that. So the idea is to calculate the ratio test, and based on that, you can say something, not always, but if the ratio is a number less than 1, you can say it is convergent. If it is absolutely convergent, if the ratio is greater than 1, then you can say the summation is divergent. Okay, and this is nothing complicated. The proof of this ratio test is basically you can compare it with, you can say, okay, an plus 1, for example, divided by an. This is some number like r, less than 1. You can create this fact that an is less than an plus 1 is less than an. Because if you multiply an r, it would be larger than that. And then what you can say is you can do this r squared an minus 1 and da 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 da. So basically what I can say is an is always less than r to the power n, or some scalar of it. And if r is less than 1, if you remember by geometric series, if r is less than 1, we can have a convergent series. If r is greater than 1, then we're dealing with a divergent series. That's basically the idea of this ratio test. Again, the proofs are all available in the book. I didn't really want to get into it. I just wanted to show you a sketch of the proof. And so let's see how we can use this ratio test. In the series, negative 1 to the power n times n to the power 3 divided by 3 to the n is absolutely convergent. You notice that the series is quite complicated. It's not that easy to say, okay, it is or it is not at the beginning. So what we can say is we can try to use the ratio test. Normally, if we're dealing with n to some power and geometric form combination of these two, normally you will go to this ratio test. This is quite often. So what is the ratio test? We just need to figure out what is the limit of absolute value of an plus 1 divided by an as n approaches to infinity. Then what is that limit? Let's calculate. Since we're taking an absolute value, turns out this negative doesn't really make any difference because the absolute value of that negative would disappear. So I'm going to ignore it and say, okay, an plus 1 would be replacing n plus 1 everywhere. So you get n plus 1 to the power 3, 3 to the power n plus 1. And an is simply n to the power 3 divided by 3 to the power n as n approaches to infinity. I can simplify it a bit. Limit 3 to the n and 3 to the n will cancel out, so you'll end up with a 3 to the power 1 in the denominator here. So you'll end up with limit n approaches to infinity, absolute value of n plus 1 cubed divided by a 3 left over divided by n cubed. And you can rewrite this a bit better. Limit absolute value of n plus 1 cubed divided by 3n cubed as n approaches to infinity. And you can cube the numerator, but the easy way would be to divide everything by an n, or you can use a, by the way, you don't really need the absolute value at this point because we dealt with all the negatives. There is no negative left. N is going toward a positive value, so I can ignore this absolute value at this point. This absolute value was necessary to get rid of this negative 1 to the power n, which I already dealt with. I didn't want to write the negative. Okay, so what do you get is n plus 1 to the power 3 divided by 3n cubed. And if you let n approaches to infinity, you can use the Hopital rule multiple times. I'm going to try to do that. Just makes it easier. Instead of you can divide an n cube everywhere. That's totally fine. Limit, so the Hopital rule, 3n plus 1 squared divided by 9n squared as n approaches to infinity. You can continue to do that. Use the Hopital rule again. Limit. It's just, for those of you who don't remember, it's just taking the derivative of the numerator and denominator separately. N approaches to infinity. Make sure that you kind of look over these materials. Derivative of the numerator would be 6. Denominator would be 18. As n approaches to infinity, that is simply 1/3. We could have done it earlier and say, okay, this ratio is simply 1, so you have 1/3. But I just wanted to show you. So what did I find? I found that this limit of the absolute value of an divided by an1 is some number L less than 1. So this 1/3 is basically the L here. We found out this is 1/3 and it is less than 1. In that case, I can say summation of an's are absolutely convergent. So I can say simply that sigma negative 1 to the power, negative 1 to the power, here we go, n times n cubed divided by 3 to the power n is absolutely convergent. That means if we take an absolute value, it's convergent. Without the absolute value, also it's convergent. That's what. Okay, how about this one? Again, it's quite complicated if you don't know this ratio test. It's figuring out the limit by itself, or decreasing or increasing. For example, what is the n to the power n derivative? That is figuring out the derivative of that would take a while. You have to remember, use the logarithmic behavior. So this ratio test is quite powerful to give you an idea if we're dealing with a conversion or divergence. So here, in this case, let's look at the, I'm going to apply a ratio test. I'll look at the limits. By the way, you notice that this is always positive. It doesn't really affect the negative or positivity. You can put a negative here, negative 1 to the power n. Maybe I should do that just to make it alternating as well. Okay, so what do I need to do is calculate the limit n approaches to infinity of absolute value of an plus 1 divided by an. And that is, okay, I'm going to keep the negative 1 this time just so you guys can see. If I replace negative n plus 1 everywhere, I get n plus 1 to the power n plus 1, and divided by n plus 1 factorial. And here, if I replace n everywhere, I will get negative 1 to the power n times n to the power n divided by n factorial. Here's the good news. The good news is you can cancel out these guys, and there's only one negative sign left, so there is a negative 1 to the power 1 left. And when you take an absolute value, that negative kind of disappears. That's the purpose of this absolute value. It makes it positive. So I can kind of say this is exactly the same as limit n approaches to infinity, n plus 1 to the power n plus 1 divided by n plus 1 factorial, and divided by n to the power n divided by n factorial. Okay, so you could have skipped over this step, but last time I didn't write it. Now I just wanted to mention it for those of you who maybe had an issue with that. Okay, so this is basically the limit of the ratio, and we need to calculate that limit. And if you don't remember what is n factorial, if you don't know that, it is 1 times 2 times 3 times 4 dot 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 up to n. So you multiply every number from 1 to n by itself. So for example, if they ask you what is 4 factorial, it would be 1 times 2 times 3 times 4. What is that? This is 24. Okay, so this is n factorial. Okay, so let me simplify that fraction. Limit, I'm going to multiply these two, divide by product of these two. N plus 1 to the power n plus 1, multiply by n factorial, divide by n plus 1 factorial times n to the power n, as n approaches to infinity. Okay, here's the good news. If you have factorials dealing with each other, you can always simplify. How can you simplify it? Think about it this way. If you have, let me go up a bit so I have space here. Let's say you have 4 factorial, also you have 5 factorial. 5 factorial will be 1 times 2 times 3 times 4 times 5. If I divide 5 factorial by 4 factorial, what is left? It is 1 times 2 times 3 times 4 times 5, this multiplication, divided by 1 times 2 times 3 times 4. All these will cancel out. The only term left is basically the very last one. So if I'm dividing n factorial by n plus 1 factorial, the ratio of these two is simply just one n plus 1 left at the end, because this is, I'm going to write it, but I will erase it just because of the space, since we don't, actually we have space, so maybe I should write it. Okay, limit n plus 1 to the power n plus 1, I'm going to write it this way. N plus 1 to the power n multiplied by another n plus 1. This is n plus 1 to the power n plus 1. The product of them, you add them the exponent. And I will tell you why I wrote it this way, just so I can simplify later. n factorial would be 1 times 2 times 3 times up to n. N plus 1 factorial would be 1 times 2 times 3 times 4 dot 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 up to n plus 1. But prior to n plus 1, there is n minus 1, and so on. And multiply by n to the power n. As I said, here's the good news. These terms are exactly here, so I can cancel them out. So I can say this will cancel out with that. For those of you that you haven't seen factorial, maybe this is an issue. So here n plus 1, and we'll cancel out with that n plus 1. That's why I separated them. So at the end of all this, what is left is limit n approaches to infinity, n plus 1 to the power n divided by n to the power n. And just to refresh your mind, you can write this as n plus 1 divided by n to the power n is n approaches to infinity. Limit, I can simplify it. N divided by n is 1, so I can write it this way. I hope you remember this. The very beginning of exponential functions, they say this is basically e as n approaches to infinity. So this is e to the power 1. This is the definition of exponential e. And what is e? E was something like 2.6, whatever that number is. And so what do I know? I know I got the limit an plus 1 divided by an. And I end up with an e, which is greater than 1 as n approaches to infinity. And what is that? That tells me the sigma here of an's must be divergent. All this work was just to show that the sigma of an, in this case, let me go back up here. Sorry. There we go. This sigma, I can say now, it is divergent. Okay. So this is quite often that you deal with such type of series to simplify, to check for convergence or divergence. So try to practice some of these. Okay, another test is the root test. I didn't check, by the way, this third option. If you end up with the limit of 1, you can't really say anything about the convergence or divergence. So if the ratio ends up 1, you gotta come up with a new idea, because this ratio test doesn't work. Okay. So I didn't write an example of that. That's simply it. How about the root test? The root test is dealing normally with examples when you have powers of n involved, something like this to the power n. So the root test is used for those cases. And what does it say? Is quite similar to the ratio test. It says if you take an nth root of the absolute value, and the result of the limit of that is a number less than 1, then the series absolutely converge. And if that nth root turns out to be a number greater than 1, then the series would be divergent, very similar to the ratio test. And if it is 1, again, it is inconclusive. We can't use this test to say anything about it. Okay, so just to clarify a bit, here's the example. So let's look at this example. Again, quite often you use the root test. Root test is often used when you're dealing with the exponents of n. In the last case, we couldn't here. In this case, we couldn't use it. You could use it here in the numerator, but in the denominator, nth root of n factorial would be quite a lot to deal with. You can't really simplify. But if there is an nth power for the whole term, you can use the nth root, commonly used in that case. So what do? We need to calculate limit absolute value, square root, not square root, nth root of absolute value of a. And we need to figure out what is that. So we need to figure out what is limit What is the nth root? I'm going to write it. Absolute value of 2n plus 3. Since this is positive, I don't really necessarily need the absolute value. If it was negative, I would erase the negative numbers. I just deal with it as positive. 3n plus 2 to the power n, as n approaches to infinity. So now we have an nth root of something to the power n. These will cancel out each other, opposite operation. So you will end up with a simple limit 2n plus 3 divided by 3n plus 2 as n approaches to infinity. And then either you can use the Hospital rule by taking the derivative. If you take a derivative, what you get is limit 2 divided by 3 as n approaches to infinity, and that's simply 2. So what we end up with is that the limit of nth root of absolute value of an was a number like 2/3 less than 1 as n approaches to infinity. If that happens, by the root test, I can say that the summation of 2n plus 3 divided by 3n plus 2 to the power n is absolutely convergent. This is the good part. When you calculate that and it's less than 1 or greater than 1, you can give the result and say, okay, this is absolutely convergent. If it was 1, we couldn't say anything. We had to come up with a different strategy. Okay, so the other case would be very similarly. You just need to calculate. If you flip the fraction, you'll end up with 3/2, for example. That would be divergence here. So here, for example, try this yourself. Summation of 3n plus 2 divided by 2n plus 5 to the power 2n as n approaches to infinity. Sorry, n from 1 to infinity. And I will tell you that this is divergent, but just try it out to see if you get that result. Okay, so this is it for this section also. I'm going to stop here. Next time we'll talk about the strategies for testing series. This would be a general case. After all these information, we kind of have to strategize how to use these tests. So I'm going to stop with this one.